So we had circles, and most people do pretty well with circles once they get a little bit of practice in. The hardest thing about the circles is making sure you got that completing the square down. We don't have to complete the square with hyperbolas and ellipses, but what makes hyperbolas and ellipses so tricky is their equations are very similar, and the vocabulary is very similar. But what makes it tricky is they have different graphs, of course, and different rules. That's what makes it so tricky to work with these two things kind of at the same time, because they have different graphs and they have different rules, but a lot of the vocabulary is the same, and the equations, of course, very similar. So it turns out that you could have something like x squared over 9 plus y squared over 4 equals 1. And you could have x squared over 9 minus y squared over 4 equals 1. And one of these is an ellipse, and one of them is a hyperbola. But the equations are almost identical to each other. So if we were to try and graph these two things side by side, kind of practice our brain to get back to where we were 12 days ago before we took a break, how do we handle this? Well, which one's the ellipse? The left one, yeah. And is this a Bert or an Ernie, a horizontal or a vertical? Yeah, it's an Ernie because the bigger number's underneath x squared. And this one, it's not about where the bigger number is to know which way the hyperbola opens. It's about which term comes first, which term is the positive term. So because the x squared term comes first, it's the positive term. Does this one open left and right or up and down? Anyone remember? Left and right, okay. But both of these, you would start by plotting the same 4 points. This one right here, the ellipse, you're going to go left and right 3, and you're going to go up and down 2. Why? Because you take the square root of the number under x squared to move left and right. You take the square root of the number under y squared to move up and down. And since this is an ellipse, we just finish it up, and we're done. The hyperbola is a more complicated one to draw. Of course it is. The hyperbola, we're still going to make those same 4 points, but then we draw that shape called the fundamental rectangle. We draw these two large slant asymptotes through the corners and through the center. And then, because the x squared came first, and we noted that this one left and right, we can sketch in our hyperbola. Just like that. What do we call these 2 points right here on the ellipse? What are those called? Those are the vertices. Does the hyperbola also have vertices? Yeah, it does. Got a vertex there and a vertex there. What do we call this line right here going across like that from vertex to vertex? That is called the major axis. What do we call this line right here? Say again?
Minor.
That's the minor axis. Good. All right, a little trickier. We learned about this at the very end of class about 12 days ago. Does anyone remember what we called that one, connecting the two vertices on the hyperbola? Transverse axis. Good. That is the transverse axis. And does anyone remember what the one going across the other way is called? Conjugate axis. Good. Conjugate axis right there. Okay. Very good. A lot of vocab there. what we can say is we can say the length of major axis is greater than length of minor axis. But over here, there is no rule about which is longer, transverse or conjugate axis. They could even be the same length. And if you don't remember that, we'll elaborate on that in a little bit. But they both have vertices, they have similar looking equations. We plot those 4 points in the same way. You can see how it'd be very, very easy to get the rules of the ellipse confused with the rules of the hyperbola and then just get some sort of botched drawing that doesn't make any sense at all. Because what happens is they both use a squared and b squared to describe the numbers under x squared and y squared. Both use a squared and b squared to describe those numbers. But for the ellipse, a squared is the larger number. For the ellipse, a squared is the larger number. For the hyperbola, a squared is the number with the positive term, not always larger than b squared. They both use a squared and b squared to describe the two denominators, absolutely. However, when you're talking about an ellipse, you look for the larger number. When you're talking about a hyperbola, if you want a squared, you look for the number that's under the first term, the positive term. And that's about where we ended up about 12 days ago. I was talking about this a squared and b squared stuff. Ellipse has two foci, C units from center on the major axis, where a squared minus b squared equals c squared. Hyperbola has two foci. Which we will learn more about later today. Okay. I can tell you this, though, right now. I can tell you this. Length of major axis, length of minor axis, length of transverse axis, length of conjugate axis. Does anyone remember what the length of the major axis is in general? I don't mean for this one specifically, but does anyone remember the rule for the length of the major axis?
It's the distance between the points that are furthest away from the center.
Yes, and is there a way we can, is there a formula for it?
Can I just add?
Well, let's think about this, everyone. Which one of these is a squared? 9 or 4? 9. That's a squared. That means that we got left and right 3 to get the major axis, right? So a is 3, and the major axis is 6 units long. So what's the formula for the major axis?
Square root it, multiply by 2.
Nice job. You square root that bigger number and you multiply it by 2. That's the length of the major axis. 2a is the length of the major axis. Now that you know that, what's the length of the minor axis? Everyone take a guess.
2B.
2b. And over here, the length of the transverse axis, give myself a little bit more room here. The length of the transverse axis is 2a, and the length of the conjugate axis is 2b. A lot of this stuff gets very, very jumbled in your brain until you start working these problems on your own. So if you're looking at this and saying, Steve, I am not memorizing this or learning this as we go. You're going way too fast and you're throwing too many vocab words at me and stuff like that. That's going to happen with all this stuff. You got to practice these hyperbolas on your own to make all these rules come together. I'm just trying to give you the rules so when you're practicing them, you can verify them by looking in the notes. But they are tricky. I would not ever give you a quiz right now and say, okay, I'm going to quiz you right now on what I just wrote on the board. No, that's ridiculous. You got to practice this stuff to learn this. Okay. Let's try this. We're going to jot down a few things about these two hyperbolas, and these are both hyperbolas because they both have the minus sign. We're going to jot down a few things about them, and then we're going to practice drawing the graphs. So first of all, do you know which way these hyperbolas open just by looking at the equation? If they open left and right, or they open up and down? It's all about the first term, the positive term. So this one, x squared, comes first. So does this one open left and right or up and down?
Left and right.
This one's left and right. And this one, since the y squared comes first, is up and down. Are we all cool with that so far? Cool?
Are they always going to be like that with the positive term in front?
They should be. The positive one should be in front. If someone writes the negative one in front and then a plus in the middle, they're being a jerk and you just rewrite them in the other order. All right, everyone write down what a squared is and what b squared is for each of these. For each of those, write down what a squared is and what b squared is. And remember the rule for identifying what a squared and b squared are for a hyperbola, because it's different than the rule for an ellipse. Because a squared is not necessarily the larger number right now. Does everyone agree with that? What is a squared? It's the number with the positive term. So in this one, it does happen to be the larger number, but that's not why it's a squared. It's because the 25 is with the positive term. And this one, it's 9. Because 9 is with the positive term. All right, let's write down just a little bit more information about these things. See if you can give, let me do that in a different color. See if you can give the length of the transverse axis and the length of the conjugate axis for both of these before you even draw the picture. Of course, when you're doing these problems on your own, you should do anything you can to get them right, except cheat, of course. So if a picture helps you get these answers, then of course you should draw the picture before you try to give them. But just in this case, I want to see if you can give me the length of the transverse axis and the length of the conjugate axis ahead of time. For this first one, what's the length of the transverse axis? It's 10. Can you tell me how you got 10? You're absolutely right.
No, you do the square root of 25, then you multiply 5 times.
That's right. Take the square root of you do square root of a squared, and then you double it. So it is 10. Very good. What's the length of the conjugate axis? 6. Take the square root of 9 is 3, double it, you get 6. Over on this one, what's the length of the transverse axis? 6. Square root of 9, doubled. And the length of the conjugate axis? 10. Square root of 25, doubled. Why did I do this example? One of the reasons I did it was to show you right off the bat that there's no rule about which one's longer. Sometimes the transverse axis is longer, sometimes the conjugate axis is longer. All right. Last thing I want us to try and do before we draw the picture is see if you can get the ordered pairs for the two vertices. In order to do this, you'll probably want to use the knowledge of which way the hyperbola opens, either left and right or up or down. It's okay to get this wrong, everyone. We're doing this in class so we can learn this together. So see if you can write down the ordered pairs for the vertices. I actually know for that first one, the vertices are going to be left and right because of the way the hyperbola opens. And I know for the second one, the vertices are going to be up and down because of the way the hyperbola opens. So I know right off the bat, when I write that ordered pair with a little plus minus in it, I know where the zero is going to go because I know which way the hyperbola opens. For the one on the left, the one that opens left-right, what number do I stick in here? Take a guess. It is 5. Because when we draw our fundamental rectangle in a few minutes here, or a few moments, we're going to go left and right 5. And if this thing opens left and right 5, that's going to be 5. How about this one over here? What are they going to be? How many units are we going up and down when we draw a fundamental rectangle? 3. So that's why it's going to be 3. Now, I'm doing this in unusual order. Usually what I do for myself is I draw the picture before I do any of this stuff. I just wanted to show you that you can do it before the picture. But I will say, usually we find this info after we graph. What we're going to do in this case today is we're going to check our answers after we graph. All right, everyone. I can't keep the graphs and the equations on the screen at the same time, so does everyone have these? Does anyone need to copy these down? Go ahead and copy down the two equations if you haven't already. Go ahead and copy down those two equations if you haven't already. And then what we're going to do is we're going to make our fundamental rectangles. We're going to put in our slant asymptotes, and we're going to sketch the hyperbolas. Does anyone need more time to copy down the two equations? Let's do this then. See if you can draw the hyperbolas for both of these. Try it. If you get it wrong, you can put a big scratch out through it and try it again later. Try it now. If you only have time to do one, you only have time to do one. That's fine. So we don't need all this dead air. Let me just interrupt you part way here. What's interesting about these two hyperbolas, the reason we're doing this example, is because they have the exact same fundamental rectangle and the exact same asymptotes. It's because if you look at the two equations, both of them have a 25 under x squared, and both of them have a 9 under y squared. So therefore, when we draw our initial 4 points, we draw the exact same initial 4 points for both of them. So they both have the exact same appearance until we actually insert the hyperbola in there. I think that's pretty cool. I think that's a pretty cool observation to make. The other thing that's interesting is just the fundamental rectangle and the asymptotes, just those pictures, are not enough to tell you which way the hyperbola opens. You have to know what the original equation looked like, because you have to know what comes first, the x squared or the y squared. So if I just put these two pictures up here and said finish the hyperbolas, you actually can't do it. You got a 50-50 chance of getting it right. But you're not for sure if you're doing it right. So you do have to know in the initial equation what came first, x squared or y squared, and that will tell you which way it opens. That's why this one opens left and right, and this one opens up and down. because this one had x squared over 25 first, and this one had y squared over 9 first. And after you get your pictures, if you go back, I think you will see that we were right about where we said our vertices were. We were right about the length of the transverse axis. We were right about the length of the conjugate axis. What else did we do? A squared and b squared, length of transverse axis, length of conjugate axis, and the vertices. We got all that right. This would be a worthwhile exercise to try again later. When you're trying to study for the test, jot down these two equations and do everything you can with them. Get some practice on your own without me up here yelling at you the whole time. Questions or comments about that? Okay. Anyone? Questions, comments, anything? It's okay if you didn't finish, but has anyone seen anything up there that they're like, wait, what? Why did you? Here are some tips for sketching your hyperbola on the exam. These are some things that you want to avoid so you don't get it wrong. Avoid sloppy asymptotes that miss corners or center. When you're taking the test, don't just draw asymptotes that just go through the box wherever you please. Make sure they're going through the corners of the fundamental rectangle and through the center of the fundamental rectangle. Make sure hyperbola touches fundamental rectangle at vertices, but don't enter the fundamental rectangle. It is very, very easy when you are sketching a graph of a hyperbola to just get kind of lazy and miss your vertex, or miss it that way. So make sure you're actually hitting the point you're supposed to hit, the vertex. Avoid this error. Finally, respect your asymptotes and put arrows on your hyperbola. Avoid this error right here. You got your fundamental rectangle. You got your asymptotes, which look great. But then when you draw your hyperbola, you just completely disregard that the asymptotes are there. You don't hug one of them or you cross over it. This one right here, let me make this more obvious. You're just kind of shooting off, not even looking at the asymptote. Or this one right here, you're not indicating that the hyperbola goes on forever and ever and ever. So respect your asymptotes and put arrows on your hyperbola to show it keeps going. As you've seen, I am not the best artist when it comes to these hyperbolas. I'm not the best artist when it comes to the ellipse or the circle either, but there are certain things we want to avoid, and there are certain rules we want to make sure we follow. Everyone can make sure they follow the rule of hitting that vertex and not going inside the box or missing it completely. Everyone can make sure they put arrows on their hyperbola to show it keeps going, and everyone can get really close to the asymptotes without touching them. So just do your best. Just do your best. Is that a hyperbola? Can the numbers be the same for a hyperbola? Yeah, all this means is your fundamental rectangle will be a square. If you were to draw this one, your fundamental rectangle is just going to end up being a square. That's a little big. We don't need it that big. Nope. I'd go up 2, left 2, right 2, down 2. Don't look at that picture to try and figure out which way this one opens. Does this open left and right or up and down? How does this one open? This one's got to be left and right. It's not the picture that tells you that. Since x squared over 4 was first, or positive is actually more important, this one opens left and right. Transverse axis and conjugate axis are both 4 units long. It is fine to have the numbers underneath these be the same. So we basically have 2 more things we need to learn about hyperbolas. 2 more big things we need to learn about them. And that is, we're going to learn a little bit more about the asymptotes. And we also need to talk about the foci, the thing that actually gave the hyperbola its shape. I'm not going to ask you if everyone feels comfortable drawing these things, because some people need to practice them on their own. But does everyone feel like you have the tools to know how to draw a hyperbola when you're practicing on your own? Does anyone need more information to help them get the drawings done? All right, let's talk about these asymptotes. Asymptotes for a hyperbola centered at the origin. There are 2 asymptotes, so we need 2 equations. If we want to tell someone what the asymptotes are, we need to give them 2 equations. The asymptotes are lines. And the way you write the equation of a line is y equals mx plus b. If you want to write the equation of an asymptote, for one of these hyperbolas, you need to write the equation of a line. both asymptotes intersect the origin. So the y-intercept is 0, 0. So b equals 0. So we just need a slope. These asymptotes for a hyperbola cross the y-axis at the origin at 0. So the only thing we need to figure out is the slope of our asymptote, because we already know the y-intercept. They actually have the same magnitude slope, except for one is positive and one is negative. So if you know the slope of one of your asymptotes, you know the other one just has the opposite sign. Which means finding the asymptotes of this thing all boil down to finding the slope of your asymptotes. If you can identify the slope of your asymptotes, you can write the equations of your asymptotes. That's it. I'm about to go back in the notes, and we're going to find some asymptotes together. Use the upper right-hand corner of your fundamental rectangle. I'm going to show you the quickest way to find the asymptotes. And it's all about using the upper right-hand corner of your fundamental rectangle. This will allow us to find the asymptote on any hyperbola pretty quickly. Pretty quickly. So here we go, back in time to our first hyperbola we drew today. Right here. Everyone, look at this asymptote right here. The one that's going uphill, the one that's increasing. A slope is rise over run. Does everyone agree with that? So look right here, everyone. What's the rise on that? To get to the upper right-hand corner from the origin, we go up 2, and over 3. Does everyone see the up 2 over 3 there? It's very important. Up 2 over 3 would be what slope? Rise over run is 2 over 3. So, the asymptotes are plus or minus 2 over 3 times x. Because you look in the upper right-hand corner, you can see you're going up 2 over 3 to get there. That means the slope of that line is 2 over 3, and the slope of the other one is negative 2 over 3. That is how we do the slope of an asymptote. We don't need a y-intercept because the y-intercept is 0. We just need the slope. I'll tell you something, everyone. These two up here have the exact same asymptotes. You can see them on there. Everyone look at this, or this one, it doesn't matter which one you look at, and write down the equations for the two asymptotes by using the center and the upper right-hand corner. See if you can decide the slope of your asymptotes. How much are you going up? How much are you going over? And write it down. Write it down so you can check your answer when we all say it out loud together. Up how many? 3. Over how many? 5. The asymptotes are plus or minus 3 over 5x. Those are your asymptotes. Are we getting them? Up and over. Don't let this one mess with you. Don't let this one mess with you. Up how many? 2. Over how many? 2. Would Steve accept this as an answer on the test? In a heartbeat, I would. What's a simpler way to write it, though?
Y equals plus or minus.
Yeah, y equals plus or minus x. But the fact that you're giving me the equation for the asymptote, I'm not going to say, oops, you didn't simplify 2 over 2. No, you're doing exactly what I told you. You looked at, how about we went up, over, and you got 2 over 2. You're a winner. That is how we find the asymptotes. That is how we find the asymptotes. You look at your fundamental rectangle. You go up. And you go over. And you get your answer. Okay. Well, shoot. I'm okay. How's everyone else doing? All right, let's talk about the foci. Every hyperbola has 2 foci. They are what gives the hyperbola its shape. It's how we define the shape of a hyperbola. The foci are C units from center in the same direction as vertices, but they are beyond the vertices, outside the fundamental rectangle. The 2 foci are found by going C units from the center in the same direction as the vertices, but you go beyond the vertices. You actually leave the fundamental rectangle. And you use this equation to find that C value. A squared plus B squared equals C squared. It's different from the ellipse. This is what you might have thought I meant to write when I wrote the one for the ellipse. This is how you find it. You add together the 2 denominators, and then you take the square root. That will give you the distance from the center to the foci. So where are they? They're like this. If you have one that opens like this, you'll have a vertex here, you'll have a vertex here, and somewhere out here you'll have one focus, and somewhere out here you'll have another focus. If it opens up and down, you'll have a vertex here, you'll have a vertex here, and somewhere down here you have a focus, and somewhere up here you have a focus. That's how you find them. We are going to practice finding the foci right now for a couple hyperbolas, then we're going to take a break and learn more about them. I just want to give you this one idea before we take a break. So everyone, I want you to do me a favor. That's a hyperbola. I want you to add the two denominators together and take the square root. I want you to add the two denominators together and take the square root. Start with one you're used to here. That means foci are 5 units from the center at 0, 0. They are 5 units away from that. The question is this. Where are the foci? At plus and minus 5 comma 0 or 0 comma plus and minus 5? Why the first one? You're right. Why the first one?
It's on the x-axis.
And why does it have to be on the x-axis?
Because it's the foci.
Good enough. What I was looking for is because you know that this hyperbola opens which way? It opens left and right. So since it opens left and right, that's why it has to be this first one. Sorry, I'm not very good at asking the leading questions. Well done, though. Well done. Very well done. All right. Do this one for me. And give me, give me the ordered pairs for the foci, and give me an exact value. No calculator. No calculator. All right, everyone. That means we're going to take a break. When we come back, we'll learn about what these foci actually do for the shape of the hyperbola. I'll see you. So, everyone, we're going to start up again. Go ahead and sketch the graph of the hyperbola that I put up on the board there. And see if you can identify the ordered pairs of the foci. This is similar to one we did before break. Not exactly the same one we did, though. So, draw a sketch for me, identify the foci, and also see if you can get the equations for the two asymptotes. It's not a trick question, it's just got a little bit more than they usually ask it. Remember, it can be a little bit trickier when that y squared comes first. Because it's still the number under y squared that helps you move up and down. It's still the number under x squared that helps you move left and right. But unlike the ellipse, the x squared doesn't always come first. So make sure you're careful when you draw your fundamental rectangle that you don't have it switched. once you're done, you can take a look up here, see if you got your asymptotes correct. By going up and over the correct amount, make sure you got them both by using a plus minus. And make sure you got the correct number for C, how far you're supposed to go to get to your foci, and then make sure you went in the right directions. Once you have that picture done, I will tell you what the foci tell us and why we have them. While you're finishing up, I'll ask this question though. Do you need the foci to help you, the student in this class, sketch a graph? Do you need the foci for that? No. So, you can find foci after you sketch your graph. We don't need them for our sketch. So don't let them take away what you already know about drawing a hyperbola. You can still draw the hyperbola even if you don't know how to find the foci. But we do need the foci because they give they give the hyperbola its shape. And here's how it works. Every point on the hyperbola is closer to one focus than the other. Closer to the focus on its side. So any point that you could find on this hyperbola is closer to the focus on its own side than it is to the focus on the other side. They're all like that. Any point on this piece up here is closer to this focus than the focus down here. And any point on the piece down here is closer to the focus down here than the focus up there. That means you have a long distance to a foci, or to a focus, and a short distance to a focus. If you do the long distance minus the short distance, you get the length of the transverse axis. Every point in the hyperbola has a distance from one focus and a distance to another focus. If you do the long distance minus the short distance, for every point, you will get the same number as the length of the transverse axis. That's actually what gives a hyperbola its shape. Here's how the book explains it, everyone. Here's how the book explains it. This is actually, if you're reading the book, this is the first thing they tell you when you start reading about hyperbolas. I don't think it's best to start with this because I think it's kind of confusing if you start with this. A hyperbola is a set of all points in a plane such that the absolute value of the difference of the distances from two fixed points is constant. The two fixed points are the foci of the hyperbola. I don't think that's the best way to start learning about hyperbolas. I think it's better to be able to draw one first. It's up to you. Maybe you would have preferred if I told you that right off the bat so you know what we were doing. But check it out, everyone. Here's some random point on my hyperbola, and it's got a distance to that focus, and it has a distance to that focus. I'll call that one D1, and that one D2. One of them's always longer than the other one. For this particular one, if you do D2 minus D1, can anyone tell me what you're going to get?
Transverse axis.
And what is the length of the transverse axis on this one? 8. That's exactly how a hyperbola gets its shape, from this definition down here. It's a little bit wordy if you have never drawn a hyperbola before and you're like, what is it even talking about? But once you draw a hyperbola and you understand the location of the foci, then I think it's a little bit easier to visualize. And that will work for every point. The reason that they use absolute value in here, just so you're clear on this, the reason they use absolute value is because then they can subtract longer minus shorter or shorter minus longer. Because if it's in absolute value bars, then you're going to get a positive answer either way. Then they don't need to say longer minus shorter. They can just say you find the difference between the two. Not a big deal, but that's why they mention absolute value and I don't. Okay, that is how a hyperbola works. That's how a hyperbola gets its shape. So, we're going to use that on the next couple problems here. Let's see here. Do we want to do another one of those? Let's do another just find the foci one. Who hates this problem? Who has a way we can make it look a little bit better? What do you want to do to make it a little better? Right, the first one over 1. Let's do that. Does that look better now, everyone? Does it look more like a hyperbola we're used to? I think so. Can you tell me which way it opens, left and right or up and down? Left and right is x squared is the first term, it's the positive term. Okay? So ski squared equals what? What two numbers do we add? 1 and 12. And don't freak out if when you add those two numbers together you get a number that's not a perfect square. We don't care if it's not a perfect square. Because we can just do this. Bingo. And once we have that, we drop in a plus or minus, we drop in a 0, and we're done. Which value in the ordered pair is going to be 0? The x or the y?
Y.
The y. Because this one opens left and right, plus or minus square root of 13. Done. Don't let these irrational numbers bother you. They're fine. They're fine. If you need to take the square root of a number that's not a perfect square, just put a square root over it. You're done. It's easier. If you were trying to find the equation of a hyperbola from some information, you need to figure out the numbers that go under x squared and y squared, and which one is the positive term. It is harder to find the equation of a hyperbola than an ellipse, because it's not just a matter of finding the right numbers and putting the right numbers in the right places. You also have to figure out if it's x squared first or y squared first. So there's one more detail you have to worry about with a hyperbola when you're trying to find its equation. So you could be in a situation where you're trying to figure out what goes under x squared and y squared, where x squared's first, or you could be trying to figure out the numbers that go under x squared and y squared, where y squared is first. With an ellipse, we always just put x squared first, put a plus in between, then put the y squared, and it was fine. But we've got one more detail we have to worry about, which is why these are harder problems. So when you're doing one of these problems with me, and we're going to do one right now, we need to pay attention not only to are we putting the right number under x squared and the right number under y squared, but do we have them in the correct order. So here's our exercise, everyone. This is enough information to give the equation of a hyperbola, everyone. This is enough information to give the equation of a hyperbola. And as I said before, not only do you need to figure out what numbers to put under x squared and y squared, but you need to figure out which order to write them in. And what is my go-to move on any one of these problems? What do I do? When I did the ellipse, what did I almost always do? To get started, to help myself. I drew a little picture. I plot the 4 points it gives me. Give me 4 ordered pairs, I plot those 4 ordered pairs. Which 2 are the vertices?
X.
The x's. Why?
It's transverse.
Because that's the transverse axis. Since the transverse axis has a v in it, that tells us that the vertices are there and there. Everyone with me on that? Which comes first, x squared or y squared, when I write my equation? X squared comes first because this one opens like this, which means it's going to be x squared over a number minus y squared over a number equals 1. I figured out which way it opened, and that's how I know which comes first, x squared or y squared. That distance right there is 3. That distance right there is 5. Does that help me? Because I went left and right 3. So under here, I put 3 squared. And under here, I put 5 squared. So it's 9 and 25. Is that cool or not cool? Cool enough for you to try one? Let's have you try one. You still don't need to mess with foci on this next example, but I'm going to just phrase it a little bit differently than I did the last one. So we're going to say vertices, vertices are at 0 plus or minus 7, and conjugate axis is 20 units long. This is not a trick question, everyone, because the conjugate axis can be longer than the transverse axis, so this is absolutely not a trick question. You can do this. Draw yourself a sketch that's just for you, that will tell you enough information to find out which way this thing opens. I won't tell you that a sketch is the only way to do this, but a sketch just helps me visualize what I'm doing. Your sketch is for you, so you put in as many details as you need. I figure out which way it opens. That tells me what if I should write y squared minus x squared or x squared minus y squared. And I figure out how far I went up and down, so I can square that number and put it under y squared. I figure out how far I went left and right, so I can square that number and put it under x squared. And I'm done. Are we happy or sad about that? Did we do okay? Anyone have a question or a comment? We're going to do a harder one next. We're going to do one where you're not given the information you want necessarily. We're going to do one where you're given the focus instead, or the foci instead. See if we can handle that. Questions before I move away from this one? Of course, will be posted as usual, but if you have a question now, I can answer it. All right, here it is. Vertices, 0, -2, and 0, 2. Foci at 0, -7, and 0, 7. Well, shoot. I'm supposed to write the equation of this. Let's see here. Vertices are up and down. So this thing opens up and down. So I know it's going to be y squared minus x squared. Just by noticing the vertices go up and down, I know that the hyperbola opens up and down, and that's enough to tell me that y squared comes first. Are we okay so far? Draw a little sketch here for myself. Don't know quite what's going to become of me on this problem, but we'll see. Vertex, vertex. Focus, focus. Let's see here. This distance right here is 2. And this distance right here is 7. Now that 2 right there, that I went up and down, that's enough to tell me that I put a 4 underneath there. But here's the problem, everyone. I know that a squared equals 4, and I know that c squared equals 49. Because c is the distance from center to focus. What can I do with those numbers? Do I have an equation that will help me find b squared? What is it for a hyperbola?
A squared plus b squared equals c squared.
It's a squared plus b squared for a hyperbola. So if a squared plus b squared equals c squared, then 4 plus b squared equals 49, which means b squared equals 45. Do I need to take the square root of 45? Do I need to square it? No, it's exactly what it should be. It's b squared. Done. Can you try one based on that? Is everyone okay to try one on their own? Let's do one on our own. Or how do you do one on your own? Okay, so we will do transverse axis is, let's do 8 units long. Vertices are at -9, 0, and 9, 0. Give the equation. This should have said foci. What in the world? Or there should have been like, what is going on? Everyone, I am so sorry. That was a bogus problem because the transverse axis and the vertices are related. So that couldn't have been done. Everyone, the foci are at -9, 0, and 9, 0. That's what I get for making up a problem on the spot. All right, try this one. Try this one. after I fix that mistake up there, how are we looking? Did everyone use the fact with the foci were negative 90, 90 to realize that this one opened up left and right? If it opens up left and right, you got to put the x squared first. Therefore, the number that goes under x squared is going to be 4 squared, because that's the distance to a vertex, because if the transverse unit is 8 units long altogether, transverse axis is 8 units long altogether, then half of it's 4, and that's your distance to vertex. Then using a squared plus b squared equals c squared, I get 16 plus b squared equals 81. Subtract 16 from both sides, I get b squared equals 65. You don't need to take the square root of that, you just put it in the equation as is. Sorry I messed up the question when I first asked it. I hope that didn't mess anyone's brain up too badly. How are we doing? Are we okay? We're going to call hyperbola's done. And now it's just up to you to do your homework and make sure you get them on your own. Let me know if you get stuck or have a question. Any comments before we leave hyperbolas behind? Okay. Nine 1 and 9.5 are our last two sections. Nine 1 you have probably seen before this class. If you haven't, that's okay. I'm still going to show it to you, but you've probably seen it before. What it is finding the ordered pair where two lines intersect, or finding the ordered triple where three planes intersect. Do not try to solve these two problems I'm about to write up here, because I'm just going to make some stuff up. And I don't have any idea if the answers work out badly or well. You ever seen a problem like that where you try to find the x and y value where those two lines intersect? That's what we're going to do. We're also going to do ones like this. The idea is you find an x and y that make both of these true, or you find an x, y, and z that make all three of these true. And that's it. That's what you do in section 9.1. 9.5, you find where two graphs intersect, where they are not both lines. In section 9.5, which will be our last section that we'll cover on Thursday, you're going to find where two equations intersect where maybe one of them is not a line. So we're going to find maybe where a line intersects with a parabola. Or, we'll do my favorite, we'll find where an ellipse intersects with a hyperbola. Like that. This will not be done with pictures, everyone. We're done with doing graphing in this unit for right now. We might do a picture to illustrate what happened, but you're not gonna do a lot of pictures when you do your homework for this. We're just looking for ordered pairs where 2 graphs, or maybe 3 graphs, intersect. That's it. That's what we're looking for. Okay. We do not find intersection points by graphing, because graphing does not work well if the answer has a fraction or decimal. So finding out where 2 graphs intersect by graphing the 2 graphs is generally not a good idea unless the person that gave you the question is guaranteeing to you that they intersect at nice integer values. Because you're not going to be able to see the difference between 4.1 and 4.2 just by a hand-drawn graph. So that's why we don't use graphing in general as a technique. The way we find out where 2 or more graphs intersect is by using either the technique of substitution or the technique of addition/elimination. I've seen it called both things. It is always your choice of what to use, but for many problems, one way works much better than the other. There's never a time in this class where I'm going to tell you you have to solve one of these problems in a specific way. It is up to you how you solve the problems we're going to do in this section, which technique you want to use, either substitution or addition/elimination, but that doesn't mean that one of them is not going to be easier than the other one. So you do want to know both techniques, but I'm not going to make you always use one or make you use another one on any given problem. So, that being said, I'm going to show you the 2 techniques right now and remind you how these work. If you are an expert at this already, you can just sit back and chill and just kind of watch. If you don't remember how to do this or it's been a while, then it's a good time to pay attention. Solve for x and y with substitution. Substitution works well when an equation can be easily solved for one variable without using fractions. Substitution works really, really well when you can take one of the equations, get one of the variables by itself without involving any fractions. For instance, it is very, very easy for me to take this equation right here and get y by itself by subtracting x from both sides. That is not a big deal. No fractions come up, and I get y by itself very, very quickly. Substitute 9 minus x into other equation where you see y. Now you substitute that 9 minus x in parentheses into the other equation wherever you see y. Looks like this. Solve for x. You all can do this problem. The way people mess this up is they just miss a negative sign, or they try to rush, or they try to do too many steps in their head. I know you all know how to solve for x. You're college algebra students. Not only are you college algebra students, you're week 13 college algebra students. So you can all do this, just don't try to rush it. Negative 7x, and I'll subtract 45 from both sides. And that's going to give me negative 7x equals negative 21, or x equals 3. Plug x equals 3 back into any equation with both x and y in it. Once you get one of your numbers, you plug it back into any equation that has both the x and the y in it. Like y equals 9 minus x. You plug the 3 in there. And you get y equals 6. Always present answer as an ordered pair. X first, y second. People mess that up when they find y first and then they find x second. If they find the numbers, the values in the wrong order, they often give the wrong order in their ordered pair. That's how substitution works. So you've probably seen that before, but it never hurts to be refreshed on it. It also never hurts to kind of keep track of what your steps are and don't lose track of what you're actually doing. Questions or comments on that? Solve for x and y using addition slash elimination. Same problem. And I'm not sure the best way to phrase this, but in order to do this technique, your equations need to be lined up. So when you look at them, they look like they're the same format. You got the x's on top of each other, the y's on top of each other, and the constants on top of each other. If you want to use this technique, you do have to have it lined up like that. Add the two equations to eliminate a variable. When I say add them, I mean you add the x's together, you add the y's together, and you add the constant together. But if, when you add them together, a variable does not disappear, then it didn't do you any good. Multiply every term in one or both equations by the same number. That's cryptic, the way I wrote that. You can use a different number for each equation. So that when you add, a variable drops out. This addition elimination technique is actually not any more complicated than the substitution one. It's just a bit more complicated to explain to people. What happens is you need to make it so when you add the two equations, one of the variables disappears. To do that, what you can do is you can multiply this equation by a number, or you can multiply this equation by a number, or you can multiply them each by their own number, such that when you add them together, a variable will disappear. Usually what you want to look for is a way to do it with multiplying one equation by a number. And usually what helps is if in one of the equations, one of the variables is negative and one's positive. So what you will notice for this one, everyone, is if you take the second equation and you multiply the second equation by a 2, then when you add them together, the x's will go away. But you have to make sure you multiply every term by 2. Then you add them together. Solve for remaining variable. Plug value back into any equation with both variables. 7y equals 42, so y equals 6. You plug 6 into any equation that's got them both, and you get x equals 3. You see how if you find 6 first, then you find 3, you might be tempted to write the ordered pair 6, 3? How easy that would be to do. You're like, oh, I got 6 and I got 3, so it's 6, 3. So please make sure that you don't do that. You put the x first, then the y. It's a really easy way to mess it up, and it's very, very frustrating when you mess up that way. So, class, these two equation, two variable systems are two lines, and we are looking for where the lines intersect. Don't try to copy this all down, everyone. I did this ahead of time because I knew I was not going to have enough time to go over everything I wanted today. But I'm putting this in your notes so you can look at it. Hey, don't let this freak you out. These are just some vocab words you might run across. Independent, dependent, consistent, and inconsistent. And basically what this is doing is it's kind of summarizing all the things that can happen. What it's kind of summarizing is if you have two equations, you're either going to find that they intersect at one point, you're going to find that they're the exact same line and they intersect everywhere, or you're going to find that they're parallel and they don't intersect at all. So you can read through this later, and this vocab will probably help with your homework. The very last thing I want to show you today is this. No one's in trouble if you raise your hand for this. How many people have not looked at the study guide or formula sheet yet? You're not in trouble. That's okay. I want to show you this, though. This is a piece of the formula sheet that I'm giving you to use on your final exam. Now you can see that it doesn't tell you everything about the circle, ellipse, and the hyperbola. But it does remind you how to figure out which way they open. How the ellipse is oriented. It reminds you of these equations, c squared equals a squared minus b squared, and c squared equals a squared plus b squared. This is why you want to look at that formula sheet, so you're not spending the next 9 days trying to memorize stuff that I'm going to give you anyway, and rather so you practice using this stuff rather than memorizing it. Everyone cool with that? So please, take a look at the study guide, take a look at the formula sheet, so you can get ready for the exam. Thank you for coming, everyone. I will see you on Thursday.